So what I have here is a regular grid of dots, and we're going to look at how those dots move in the image plane of a camera as the camera moves. So here we have the camera looking at that grid of dots, and I'm going to move the camera towards the left. That's the negative X direction. And we can see that the dots all appear to move in the positive X direction in the image plane. Come back to the middle, and now I move the camera in the positive Y direction. We see the dots all appear to move upward in the frame. That's in the negative Y direction. If I move the camera downwards towards the plane of the dots, we see that they all tend to be expanding outwards from the center of the image plane. And finally, if I rotate the camera around its Z-axis, what's called the optical axis, we see that the dots all appear to rotate around the center of the image plane. Consider that we have a camera looking at an object, in this case a ball. We attach a coordinate frame to the camera, a way that we should be quite familiar with now, and we call that coordinate frame C. Now we can define the position of the ball with respect to coordinate frame C. Now we can consider that the camera is able to move, and it's moving in three-dimensional space, so it can have potentially a velocity in the X, Y, and Z directions, and it can rotate about the X, Y, and Z axes. We can project the three-dimensional position of the ball into the image plane, and we obtain the coordinate u, v.
Let's demonstrate some of these ideas in MATLAB. I'm going to create a camera object, and we've encountered this before. It's a pinhole camera with default parameters, and these are shown here. And I'm going to create a point in the world. It's going to be X coordinate of a meter, Y coordinate of a meter, Z coordinate of 5 meters. Transpose that so that it is a column vector. Now I can project that three-dimensional world point onto the image plane of my camera, and it is at this coordinate, 672 for U, 672 for V. Now I am going to project the point again, but this time I am going to shift the camera. I can do that with the TCAM option, the transform of the camera, and I am going to move the camera 0.1 meters in the X direction. So the transfer function we've encountered before creates a homogeneous transformation that represents a translation. There is no rotation in this, a translation of 0.1 in the X direction, 0 meters in the Y direction, 0 meters in the Z direction. Close that last bracket off, and here's the point. So I have moved the camera a small amount in the positive X direction, and we can see that the U coordinate has reduced. The point has moved toward the left in the image. I can compute the sensitivity of this motion by taking the difference between the shifted point and its original position and dividing by the amount that I move the camera. This sensitivity indicates that for every meter that I move the camera in the positive X direction, the projection will move minus 160 pixels on the image plane. We can repeat this process for other kinds of camera motion. So here's our projection function of the world point, and I'm going to now translate the camera in the Z direction. Subtract the original position and divide by 0.1. And here we see that if I move the camera 1 meter in the Z direction, this particular point will move 32 pixels in the U direction and 32 pixels in the V direction. I can replace that translation with a rotation. So let's rotate the camera, say 0.1 radians around the X-axis, and repeat. And in this particular case, the projection of the point will move by 40 something pixels in the U direction and 850 pixels, significant amount of motion, in the V direction. So what we've seen is the relationship between how I move the camera and how the projection varies on the image plane. A more intuitive way to visualize what's going on here is to display the flow field. And the flow field is defined for this particular camera, and I pass in the velocity of the camera. So in this case I'm going to pass in the spatial velocity of the camera, so it's a 6 vector, and it has got unit velocity in the X direction. And so the flow field looks like this. It's saying if the camera is moving in the positive X direction, then every point in the image will be shifted towards the left. If I change the camera velocity to be unit velocity in the y direction, then the flow field looks like this. So if my camera is moving in the positive y direction, which the way I define my camera coordinate frame, the camera is moving downwards in the world, then every point in the image appears to move upwards. Now let's change the velocity to being unit velocity in the z direction. Imagine the camera is moving towards the scene. Now the flow field looks like this. We have this very distinctive radiating pattern coming from the center of the image plane. The final example that I want to show you has got 0 translational motion and it has got unit rotational motion around the z-axis. So I'm rotating the camera, and in this case every point in the scene appears to rotate around the center of the image plane. Let's consider that we have a regular array of points and the camera is moving in the positive x direction. It has got a positive x velocity component. What we observe is that all the points in the image move uniformly toward the left. Now let's consider a more interesting example where the camera is moving forward. And now what we see is this interesting radiating effect, a bit like the Star Trek warp speed effect. We see that points towards the edge of the image are moving faster than points in the middle of the image. The center of the image we call the focus of expansion. It's the point from which all of the pixels appear to be radiating from. Consider now that we rotate the camera in a positive direction around the z-axis. If I'm holding the camera, that would correspond to me rotating the camera in a clockwise direction. The pattern of pixel velocities is now quite different. We see that each pixel's velocity is tangential to a circle centered on the middle of the image. So far we've considered a fairly contrived example. We've imagined this camera moving towards a uniform array of dots. The real world is not like that, but we can compute this optical flow phenomena for real image sequences. Here we see some imagery which is captured from an unmanned aerial vehicle, a flying robot if you like. The robot is flying at pretty much constant altitude and moving in fairly much a straight line. Each of these green arrows indicates the direction that a point in the image is moving from one frame to the next. This pixel motion has been greatly exaggerated. From frame to frame, a point is only going to move a few pixels. Although the average pixel velocity is downwards within the image, we can also see that there is some side-to-side motion, and this would indicate then that the robot is not exactly flying a straight line path. Perhaps it's being buffeted by wind gusts, which is causing its heading angle to change a little bit. Another example, this one which is more three-dimensional, is taken from a camera on a car moving along a road, and there are a lot of parked cars at the side and there are a lot of trees. What you'll notice in this particular case is that objects that are far away cause relatively little optical flow, where objects that are close by cause a large amount of optical flow. We can see this radiating optical flow pattern again. We can see that the vectors all appear to radiate from a point in front of a car, which we call the focus of expansion. That's the point in the world that the car is heading towards. Another thing we'll notice occasionally is that the optical flow vectors bounce up and down crazily, and that's because the car is driving over a speed bump. So the car is pitching up and then pitching down, so that causes an additional motion component, which is superimposed on top of the optical flow due to just pure forward motion. This is a very, very powerful illusion. I'm inside a rotating drum and my eye can detect the motion of this drum. My eye and my brain are computing what we call optical flow. And this optical flow that's caused by that rotating drum is the same sort of optical flow that I get if I rotate my head this way or I rotate my head that way. And this particular illusion causes me to feel a little bit uneasy because the information that I get with my eyes, the optical flow, tells me that my head's moving from side to side, but the gyroscopic sensors in my ears tell me that that's not happening. So there's a disconnect between what my ears are telling me about my attitude and what my eyes are telling me about my motion. And that leads to the sensation of seasickness or slight nausea, which is why I'm hanging on very tightly to these rails.